I really thank everyone for coming and for Dr. Ahmed Ataya initiating the invitation for coming here. And I'm glad to see all of you here that I have communicated with you so many times over the years. So we'll have today 3 different lectures. This is the first one. I specifically started. Can you hear me okay? So I think you can hear me now better. Yeah, okay, good. So again, I really thank everyone for coming and for this opportunity to be here with you after maybe 4 years not coming to Egypt. Yeah. So as I was mentioning, I have 3 talks, and I think the other 2 talks are consecutive to each other. The second talk would be basically about finite difference time domain and its applications. And then the last one would be one of the main application of the finite difference time domain, in which we are studying the interaction of electromagnetic waves with the human head. So I keep these 2 talks at the very end so that one would be after the other. This is a completely different talk. So I'm going to talk about this first, and then we'll see how the other ones will go. Please raise your hand at any time. Interrupt me at any time. This is not a traditional lecture that I have to, or talk that I have to talk, and then we'll keep the questions at the very end. I would like to have some sort of interaction all the time. So it's helpful for me as well, and I always learn from the questions. So please ask questions as much as you can, okay? Most of the work here in RFID area I started to learn about RFID in 2009. And I spent about 3 years going back and forth between Mississippi and Finland. There is a group in Tampere University of Technology. I spent a sabbatical term over there, and I sent the students over there from my group to learn about the technique. And from 2009 on, we started to work with finite difference time domain. So it's not something that I started to work on it early on. My PhD and background was basically in a completely different area, which was basically scattering and diffraction of electromagnetic wave by edges and wedges. And then we had to migrate to some other areas and so on. That's really mentioning this because those who are just graduated or just got their PhD, you have to keep in mind that what you did in your PhD is something useful. You deserve the PhD degree for this work, but keep in mind that you have to work in this area and in other areas as well. You can't continue work on your PhD topic, otherwise you are not going to make good progress in the future of your academic career. So I had to do this, or I forced it to do this to be able to survive in the department that I was in at that time. My first sabbatical, for example, was at UCLA, and I learned how to start working with antenna. I never designed an antenna before. I started to work with antenna since 1996. I started to work with RFID since 2009. Computational electromagnetic is something that I'm heavily involved in right now. We have 2 books on it, and that's something we started to work on it in late 80s, early 1990. So this is basically the 3 topics that I heavily worked on right now is basically computational electromagnetics, RFID systems with integrated sensors, and antenna design. And we do antenna designed for all kinds of applications, small antenna and large antenna and so on. So let's talk about RFID. So I'm gonna start with a brief introduction, and then the technology behind the RFID system, and then how does it operate and how does it work. How this mouse is gonna work first. Do you think a mouse would work on an LCD? Okay. No, I mean the laser pointer.
The laser pointer is not appearing because of the...
That's what I'm thinking, yeah. So...
Actually, you can go to the screen.
I know. I was looking for mechanical pointer, the old-fashioned way, but but let me get a pen or something so I can point with it. Okay, at least a pen would work. I'm not going to touch the screen, so don't worry about this. So we're going to talk about a little bit of introduction, the technologies behind RFID, and then we are going to focus on UHF RFID system and how does it operate. And then I'm going to show you some designs for antennas for RFID readers. And most of the work here is conducted by one of my PhD students who is currently finishing his PhD. And then I'm going to show you some applications that we have conducted using RFID, at least 2 applications that we have recently worked on. So starting with where does the word RFID came from? And it's basically, as you see it here, radio and frequency identification. And that's basically the 4 letters that makes the word RFID. And the key point in all this is that we are using RF signal. So that's basically the main objective of what we're doing here. So I'm sure you have used RFID in one way or the other. And this is basically a very simple illustration of embedded RFID tag near field communication with this reader here. And there are also hidden RFID tags as well with integrated chip that most likely in those paper kind of stickers, you don't see them there, but they are there and they are working as an RFID system, with an RFID system. So we are going to talk about readers. For example, this is the device that reads the RFID tag that's inside here, this card. And we can use all these type of RFID system for building access and many other identification, and we're going to talk about this in industry and medical application, military application, and so on. So this is basically what I would like to show, is that we can use it in transportation, in retail stores, defense or military application, and health care system as well. And now, with this very brief introduction, let's see how the RFID technology has been developed and what are the components of an RFID system. We have 3 components: the tag, which we talk about it most, and then the reader that reads the tag, and then the host system, which is basically computer or embedded system that basically collect information from the reader, process it, and using software and all other applications. So the tag itself can be an active tag, can be a passive tag, or semi-active tag. So Dr. Asmat and I were talking this morning about sensors that has batteries that are very hard to replace the battery into them. So if we use semi-active tag or passive tag, we can charge those batteries remotely, and we don't really have to basically replace the battery itself. The sensors that we talked about, it was not RFID sensor. I'm going to show you here 2 different types of RFID systems with integrated sensors that can be used. This is not the only 2 sensors that can be used, but there are so many other sensors that people have used with RFID systems or RFID tags. the reader itself is basically the one that interrogates the tag and then reads the tag. And we can also write to the tag with these readers. Can you still hear me or not? Okay. And so basically, we can send data to the tag, and those readers could be fixed readers or could be handheld readers or small readers or development kit that I'm going to show you. Some of the applications that we have been doing is basically we use RFID development kit. Basically, it would be a circuit board that has input for antennas, and those antennas are going to communicate with the tag and connection to a computer, and you can program them and you can put your application into them. So the system in the most simpler way is basically, as you see it here, we are going to have a tag, and the tag is going to communicate with the reader, and the reader is going to communicate, if it doesn't have an embedded system, is going to communicate with a host or computer to process the data itself. The tag is not going to respond to anything until the reader is sending a first signal to the tag, and then the tag is going to respond to the reader and so on. Anything in between or close by to the tag is going to have reflected signal or scatter signal from it and going to affect the tag as well. So those are conditions, or those are things that we have to take care of it as well while we're building a system. So if we look at the different types of RFID system all over the world, we can see that there are three categories in United States or North America. We are basically from 900 to 930 megahertz operation with center frequency 915. In Europe from 860 all the way to 870. In Japan from 950 to 956. So roughly, if you look at the entire range, if you can start here from about 860 all the way to 960 in the megahertz range, that's basically the range that you can have tags to work in one of those three ranges. You can have readers designated to each one of those areas, or you can have readers that has the capability to read tags in most of these three areas. So there are readers that can work in any of these systems, but most of the time, the tags themselves are not designed for three areas. They are designed for a specific region. So if you look at the tags, early on we have low frequency tags, and that use inductive or capacitive coupling between the tag and the reader. The first card closer to the reader is basically an inductive capacitive or coupling reader that you have seen it in the second or third slide. 13 megahertz to 56 megahertz also is using inductive coupling. And then the most common application for the last few years and still coming right now is UHF tags. Recently, there are tags that are working beyond 960, 2.4, even all the way to 6 gigahertz. And so there is so much work is being done right now to extend the capability of the tags and the reader beyond 960 megahertz. And the difficulty there, or the lack of system components, is basically the reader for any frequency above 960. And most of the research work that's being conducting right now is to use software-defined radio, especially the handheld software-defined radio, to basically build an application with them so that you can change the frequency. Those handheld SDR can work all the way to 6 gigahertz. And if you can build a reader from the software-defined radio, that would be the most efficient way to communicate with tags. We can create tags at any frequency. Tags can be created at 2.4, 5, or 6 gigahertz, but the readers are basically the lacking technology right now. So looking at how far can we read the tag, you can see the coupling. If it is inductive or capacitive coupling, we can't exceed our limit is basically 1 centimeter separation between the tag and reader. If we're using this high frequency, we can reach up to 1 meter. For UHF, it's much larger than 1 meter. How much larger than 1 meter? We can reach up to 10 to 15 meter using UHF. It depends on how good is the tag is designed. And another key factor is the integrated circuit that's connected to the tag. So the integrated circuit, the electronic companies and the electronic that makes the integrated circuit is the major component in this application here. Obviously, if we increase the frequency, we are going to be able to reach further distance for reading. And again, there is another factor that control all these 3 parameters here. If our tag is active or semi-active, the range is going to be beyond maybe 10 meters as well. I gave this lecture a couple of days ago in the Wales University, and someone asked me, can we read tags 5-6 kilometers away? And I told him, I haven't seen anything like this yet, but maybe in the future. But I don't think we can reach 1 kilometer read range, even with active tags, but maybe 20 meters, 30 meters is basically possible read range for active tags. There are some standards that are being set up with the RFID system. Specifically, if you go to higher frequency range, you can see here at 2.4 and 5.8 gigahertz. And you can see that there are 2 acronyms that are usually used, ISO and EBC. This is basically International Organization of Standards, and then Electronic Product Code. And you can see so many numbers and indication about the progress of the ISO and EBC. So when you have any reader on the market, you are going to see that the reader is defined in terms of ISO and EBC as well. And the tags are going to be, and you can see here, EBC is defined as generation 1, generation 0, and generation 2, and so on. So those are the things that characterize the readers and what kind of tag that can be read. An old reader may not be able to read new generation of tags, and so on. So again, how does the generation, categorization of the system itself? We talk about the communication between the reader and the tag. The tag itself could have a chip or integrated circuit, or we can have tags with no integrated circuit at all. And the tag can be active or passive. And then the frequency range, we talk about those frequency range, low frequency, high frequency UHF. This is the most common one. And then there are tags that are designed for short range or long range. And the ones with very, very short range use magnetic or electric coupling. Now, coming back here, the communication protocols are full duplex, half duplex, or sequential. And these are, I'm sure everyone knows about those kind of communication between 2 devices. The chip is basically the tag that has an integrated circuit. Chipless RFID tag is basically a pure antenna that's been designed that doesn't have any integrated circuit. The regular UHF tag that has an integrated circuit, it does have the capability of storing some information about the item that's being connected to. When we have a chipless RFID tag, it depends on the design of the tag itself. We can figure out how many items or how much range of information we can store. Most of the time is much less information. We can store it in a chipless RFID tag, and I'm going to show you why. But the capability of tags with a chip is that you can store information, you can read you can store the information, you can erase it, you can rewrite it, and so on. And any tag in any system is basically having a unique ID. So if you have multiple tags, there is usually any tag has an identification ID that's different than all other tags. This is a quick illustration about half duplex, full duplex, and sequential as well. I'm going to skip this because I'm sure every one of you knows this information. here is some images of tags. This is, for example, an RFID tag with a chip. These two are RFID tag with no chip. These are also passive tags. This is the alien type tag that's very common. And this is an RFID tag with a battery, an integrated circuit, and we can call it semi-active tag. I'm going to give you the difference or show you the difference between semi-active tag and an active tag. And you can see the active tag is most of the time is larger, encased into a case, and most of the military and medical application using active tags. Okay, so how the RFID tag types, different types, how do they operate? So on this side here, I'm going to have the tag. And on this side here, I'm going to have the reader itself. The reader is going to have an antenna. For the passive system, the antenna is going to send the signal, as you see it with the green color here. This signal is going to be rectified in this scenario here in the tag. Part of it is going to be converted into a DC power to turn on the chip. Once this is done, there will be a reflected signal from the configuration of the tag, and this reflected signal is going to carry the information that's inside the chip, and the reader is going to read this information here. And then basically the host is going to process this information. Now if we have semi-active tag, then we're going to have a battery connected to the tag itself, and this battery is not going to be connected to the chip, is not going to make the chip on all the time. The chip is off until this signal comes on. Then the battery is going to activate the chip and the integrated and whatever circuit is here, and then send signal back to the reader and then the host media. So in this scenario here, we have semi-active because the battery is not on all the time. It is only on when the tag is triggered by the reader. In this scenario here, you don't see a green wave because the battery is connected to the tag and the battery is on all the time. When the battery is on all the time, then this tag is sending a signal all the time, whether we have a reader here or not. So basically, you install those kind of active tags in an area where you have continuous monitoring or real-life monitoring of people coming in and out in a secure area, for example, or products that you need to know exactly where it is located all the time, and so on. Obviously, if you are using active tag, each tag is going to reach or could be between $20 and $100 each tag itself. For the passive tags, it can be only 10 cents or even smaller than this. Many years ago, there are lots of work was being done to make this. This is 10 cents. They wanted to make the tag cost less than 1 cent. So there are two components in the tag, the integrated circuit cost and the tag itself. So the fabrication of the tag, the material that makes the tag, and the integrated circuit was supposed to be less than 1 cent. Right now, I think you can get tags for about 2 cents instead of 10 cents, but in quantities of 100 or 200 or 300 and so on. The semi-active tag is just basically in between, so you can get semi-active tag all the way to $20 each. And then the read range, obviously the read range for the active tag would be much longer. This is in between, and this is less than 20 meter. I haven't seen any application with passive tag that reach 15 meters active application with all the time. So to give you an indication about some of the tags, you can see if this is a grain of rice, this entire thing is basically what's between these two fingers here, but expanded just to show you the size of it. This is one of the well-known passive UHF tag with an integrated circuit here. And you can see in most of the UHF tags, there is a loop around the integrated circuit. And this loop is basically acting as an inductive matching circuit for the chip. When we build an antenna, we always build the antenna for a 50 ohm system because our network analyzer has an input impedance of 50 ohm. When we design the antenna like this, when I talk about antenna, is basically everything you see it here, except the chip itself is basically an antenna. So the two ports here that you can connect something to it and connect it to the network analyzer to see the input reflection coefficient of this antenna, that's going to be a reference to a 50 ohm. When you put a chip on it, the input impedance of the chip is not 50 ohm. Most of the time, it is capacitive with range between 100 to 200 reactive part, and the input resistive part is in the order between 13 to 18. So it's a completely different input impedance of the chip. So you really need to have the input impedance of the antenna have a little bit of loops to provide some sort of inductive reactive part to compensate for the capacitive reactive part of the chip. And the impedance itself is not going to change much, but basically most of the UHF tags, you are going to see a loop around the chip to compensate for the capacitive part of the integrated circuit. Okay, those tags also can be designed for near field operation or far field operation. And I'm going to show you an example of an antenna connected to a reader. And this antenna has the capability to sense the tags in the near field or in the far field as well. So here is an illustration of mini UHF RFID tags. You can see the loop is here, over here, and you can see looping structure in terms of aperture here, and so on. Some of this you can see how this matching network here, matching network here, and so on. Some of these tags, like this one, you can see 3 branches or 3 arms, this one as well, this one, and this one. They are circularly polarized tags. Most all other are basically linearly polarized tag. When you put a tag on an item, if you put the tag in this direction, then you have to have an antenna either linearly polarized with the same polarization to be able to read it. If your polarization is in 90 degree out of this tag here, then basically you're not going to read anything. In between, you're going to have fractional reading. But if you have circularly polarized antenna connected to the reader, then you are going to be able to read this tag, whether this tag is in this direction or inclined a little bit in every direction. So good readers, they have circularly polarized antennas to avoid the fact that the tag could be oriented in any direction, especially if this tag is connected to an item that's moving or oriented in different direction, then you can still read it. Instead of having linearly polarized tag, sometimes we design circularly polarized tag. So basically the circularly polarized tag, circularly polarized antenna, the communication would be much better and the read range would be longer as well. Yeah, this slide is just to mention again that traditional conventional UHF tags, they have integrated circuits. Chipless RFID tags, they don't have any integrated circuits. And this shows you the number of papers that's being published all the way to 2020 for chipless RFID tag and chipless RFID tag to a sensor. You can see the trend of these two curves are basically straight line going up, and you can project this for 2021, 2022, and so on. So it's huge number of research and papers are being published about chipless RFID tag. And the reason for this is basically simply going away completely with the integrated circuit, making the tag much, much cheaper, and making the tag on a flexible material where you can bend it or conformal to other objects, and so many capabilities that you can get, but you lose the functionality of storing large amount of information in the tag. So here is an example of chipless RFID tag. This entire thing is one tag. And the difference between this element and this element is basically the gap between the two dipole antenna here. So this small gap here that keep increasing is going to make this entire object resonate at a little bit different frequency. For example,